in this very first example involving a statically indeterminate structure, we've got several things that are going to happen that are different than we've ever done before. Usually when we try to find stresses in rods and that sort of thing, we can just use the equations of equilibrium alone to find out what the force is in the particular member, and that's no longer going to be the case. We're going to have to do some other things beyond static equilibrium, because the whole notion of the indeterminate means static equation of equilibrium are insufficient. So let's go and look at a free body diagram of this rigid bar ABCD that has two flexible rods, the aluminum rod and the steel rod, that are helping to support it. And let's consider a displaced shape. If that bar is rigid and these rods are flexible, then under small deflection theory we might anticipate that the deflected shape might look like this. And when I'm making these big deals about saying small deflection theory, D is going to go down directly. I know it probably swings as an arc, but it's so infinitesimally small, as we talked about in the previous example, with this almost a nearly identical system that was back when we didn't have this rod C here, that went down only a little bit and went left and right even a lot less. So that's the small theory part of this, that this looks like a right triangle in our model. Right? And if we look at it that way, we realize that, okay, here's delta B from that center line axis down. There's delta C, center line axis down, and then delta D, same thing. There's that. Hey, that means that the aluminum rod was elongated, stretched, and that means when we cut it away, it's pulling on the system here at B, and that's our axial force in the aluminum. At C, the steel is getting squished, so that's compression, and then we've got the applied load P out here in the end, which in the problem statements is 5 kips. Now we also have the reactions at A, AY, and AX. So note that R is equal to 4. That's 4 unknown quantities here, and we only have 3 equations of equilibrium. That's what makes this statically indeterminate to the first degree. That doesn't mean we can't find some of them. For instance, sum of forces in the X tells us that AX is going to be 0. Well, R now goes down to 3 and N goes to 2 in terms of the unknowns. So because we burned one up to even find that trivial answer. Right? So statically indeterminate to the first degree. Now, what's making this indeterminate in some sense is the fact that we have these two flexible things. If we only had one, that goes away, and now we're statically determinate. We can find the force in the aluminum without having to resort to other things. Right? So in a sense, these things are the indeterminate things. So let's write an equilibrium equation that involves them. That means let's sum moments about point A. Get rid of AX and AY. We don't need them. I'm going to take clockwise positive because that's the same tendency to rotate the body about in a counterclockwise fashion. And so when we do that, we'll have this moment arm that is 12 inches for the aluminum, so 12 inches times NAL plus, and then the steel is located here at 24 inches out, and there we go there, plus then we go all the way out and we have a 30-inch times 5 kips. Now note, it goes in the other direction, so that really needs to be a minus sign, and we'll set that all equal to 0. That's a big equation. We can leave it like this if we want. We could also simplify it slightly by dividing by 12, and 12 inches even, and we'd have then something that would look like this. Right? 30 times 5 is 150. 150 divided by 12 will be 12 and a half, or you could look at it as ratio of 30 to 12 is 2 and a half, and 2 and a half times 5 will get us also the 12 and a half kips. So that's the equilibrium equation, one of them only, 2 unknowns, and so we need to do something else. And that comes partially at looking at these displacements. Right? Here's this displacement pattern. Notice this right triangle that's formed, and so we have similar triangles. And that tells us right off the bat that delta C is going to be twice as large as what delta B is. Also tells us that delta D is going to be 2.5 times as large as delta B, right? 12 and 24 here, so 24 is to 12, that's the 2 to 1 part, and you've got 30 is to 12, that's going to give us the 2.5 factor, right? This is going to be key, and since these two are the one that is going to end up relating our aluminum and our steel, those are the ones that's the specific one that we're really going to want to have and work with, right? So now, additional part of how this is going to work is we're going to deal with the axial force displacement relationship, delta equal NL over AE, or I like to do this as N over K, where K is equal to EA over L. That's the axial stiffness of the member. So let's go get it for the steel. That's going to be EA over the L for the steel. That's going to be 29,000 kips per square inch times the area we're provided is 0.2 square inches divided by that length of that rod, that's 10 inches. So kips over square inches times square inches leaves us kips or forces, and force over inch is going to be a stiffness rate. And so that'll be 29,000 times 0.2 divided by 10, or 580 kips per inch. Right now, K of the aluminum also is EA over L for the aluminum, and that one was, see, E is 10,600 KSI for this particular one. It is 0.8 square inches of area divided by its same length of 10 inches, and that's going to be 848 kips per inch. So the aluminum rod is actually stiffer than the stiffness of the steel, even though materially the steel is 3 times as stiff as the aluminum is. So it's the combination of all of this EA and L that matters in terms of the various values of stiffness. Right? Now going back to the compatibility here, we found a displacement relationship that was delta C is equal to twice delta B. Right? Now, that's really what we call a compatibility equation, that in order for this to work right, the displacements have to relate to each other in that way. Now note, if delta B goes downwards, then the rod has elongated, and that means that we have this tensile force in the rod that's shown as this free body. This is all delta B positive, means an elongation of the rod, and the force here in the free body diagram is consistent with that. That tells me that delta B is the same thing as the deformation of the rod. Now, one of the reasons why that might change is if there's a gap here before that ends up then connecting and elongating something, or if the end of the rod, the top of the rod, were to displace also, maybe by the same amount as delta B, then that would be a zero deformation. So you have to be careful about the linkage between a global displacement and what happens inside the member. In this case, it's fairly straightforward, and the same thing is going to be true over here at C, that if the steel is going to shorten, then okay, it's in compression, and that and we've got that force already like that, and that's consistent with the positive delta C that we've got showing. Right? So we've got to be very careful about how we're managing all that. And now note what's going to work. We've got the global displacement compatibility equation now in terms of the internal deformation of the member. Internal deformation model is going to be a stiffness relationship here, NL over AE, so we get the NAL over KAL, and we have over here steel, N steel over the K steel. And so now we could solve that in terms of one of the two. I'm going to do it in terms of the steel. So 2K steel over KAL. This has all been symbolic. Let's get this in numbers. The steel is got a stiffness of 580 kips per inch. The aluminum has 848 kips per inch. So those units are going to go away. And then times NAL. Wow, I've got one force in terms of the other That's exactly what we needed, because we were back here with the equilibrium equation and it had two unknowns in it, but it was only one equation, and now I have one in terms of the other because of the force displacement and the compatibility relationships. So now we can come back and say, alright, NaL plus 2 times N steel is equal to 12.5 kips, and now we start substituting in. We got NaL plus 2 times 2 times 580 over 848. I chose to leave this there because we got this 2 that comes in twice. One from compatibility and one from the equilibrium equation. And that can sometimes be a little confusing there. And so now we get all of that. And you see that that would become 1 plus 2.74 times NaL equals the 12.5. And so plus 1 in there, take the reciprocal of it, times 12.5, and we find out that the force in the aluminum rod is 3.34. Remember, you round at the 5s, you round down to the even number if that's what's there. That's kips, that's an important one. And then of course we go back from the relationship that we have up here, that the force in the steel then is 2 times 580 over the 848 times the 3.34. And we find out that the force in the steel is 4.58 kips. Alright, just keeping 3 digits around as typical of engineering work. Alright, so we were asked to find the stress on the 2 rods and the deflection at point D. So let's go get first a consistency check and calculate stresses all at the same time. The stress in the steel is equal to the axial force in the steel divided by the area in the steel. That we just found out was 4.58 kips divided by 0.2 square inches, and then that will give us a stress of 22.9 KSI. That is in compression, and that is less than the 36 KSI yield stress, so therefore that's okay. That's a linear elastic behavior. Right? Now that doesn't include buckling, so we're not going to include that part. Later in the semester we will. And then we go do this for the aluminum. And we'll have then 3.34 kips over 0.5 square inches. And that will give us a stress value 0.8 square inches of 4.2 KSI in tension. That's much less than the 60 KSI yield for the aluminum. That also is good. Right, so that gives us everything we want there. Now we were asked to find also the displacement out at the tip. We haven't done that. Now if we're not elastic, then none of this model is correct and we have to do something else. That's something that will be explored in the next example. All right, let's get delta D. That's equal to 2 times delta, well, sorry, no, it's not either. It's equal to 5 divided by 2 times delta B, and delta B is equal to the delta of the aluminum, and the delta of the aluminum is equal to N of the aluminum over the stiffness of the aluminum. Notice how this is all nicely working out, and we know, I could have done NL over AE here, but I already have the stiffness, so why not work with it? And the value of the aluminum force is 3.34 kips. Stiffness is 848 kips per inch, so kip over kip per inch is going to give us inches, and so we get then a very small value, 0.00986 inches. I already got the times 10 to the minus third in there already taken care of. So about 1/100th of an inch is the displacement. So delta D approximately is 0.01 inch going downwards.